Welcome viewers. We know that flux of electric field E through an area element delta S can be written as phi is equal to E delta S cos theta, where theta is the angle between direction of electric field and normal to the area element. If area element delta S is placed normal to electric field, this is your delta S and it is placed normal to electric field. So, angle between electric field and normal to the area element becomes 0, theta becomes 0 and cos 0 is 1. So, your flux becomes maximum, that is E into delta S, and if area element delta S is placed tangential to electric field, this is your area element and electric field is like this. So, angle between normal to the area element n cap and electric field is 90 degree. So, cos 90 is 0. So, flux will be 0. We also know that electric flux is proportional to total number of electric field lines passing through any surface normally. Now, as the source of electric field lines is a charge, so a German mathematician and physicist called Friedrich Gauss thought of a relation between total electric flux passing through a closed surface and amount of net charge enclosed by the closed surface, and he ultimately found it, and this famous relation is named after him and is called as Gauss's law in electrostatics, which is the topic of discussion of this program. Let us try to find electric flux passing through a sphere of radius small r. Suppose this is a sphere of radius small r. Let charge plus q is placed at the center of this sphere. Now, to find the net flux of this sphere, we may cut a small area element delta S from the surface of this sphere. Let us suppose this is a small area element delta S. So, the flux through an area element delta S is given as delta phi E dot delta S, where electric field due to this charge at this point is 1 by 4 pi epsilon naught q by r square multiplied by r cap Suppose the magnitude of this particular area is delta S and the direction of area is taken as in the direction of normal n cap. So, delta S vector can be written as delta S multiplied by n cap. So, we can put here dot delta S n cap, where we have used Coulomb's law for the electric field due to a single charge q. Now, since the normal to a sphere at every point is along the radius vector at that point, the area element delta S and r cap have the same direction. So, we can write delta phi as 1 by 4 pi epsilon naught q delta S divided by r square, because r cap and n cap both are in the same direction. The total flux through the sphere is obtained by adding up the flux through all different area elements which can be cut from this sphere. So, the total flux will be sum of all delta phi, sum over all delta S, and summing over all delta S we can put here. So, we can take 1 by 4 pi epsilon naught as common, Q is constant, we can take it out. Again R square is also constant for all the area elements which are cut from the surface of this sphere, and summation delta S, and sum of all the area elements which can be cut from this sphere will give you the total area of this sphere. So, what do we get? We get phi is equal to 1 by 4 pi epsilon naught Q by R square multiplied by sum of areas of all the area elements, which is equal to the area of the sphere, and area of the sphere is, all of us know that it is 4 pi R square, and solving it we get Q by epsilon naught, which is the total electric flux coming out of the surface of this sphere. Final result obtained is a simple illustration of a general result of electrostatics called as Gauss's law. We state Gauss's law without proof. Gauss's law states that electric flux through a closed surface S is equal to Q by epsilon naught, where Q is the enclosed amount of charge enclosed by the surface S, that is the flux of electric field through any closed surface S is equal to 1 by epsilon naught times the charge enclosed by that surface. The law implies that the total electric flux through a closed surface is 0 if no charge is enclosed by the surface. That is, if Q is 0, you can see, because phi is Q by epsilon naught, and if charge enclosed by the surface is 0, this implies flux passing through the surface will also be 0. Let us check by taking an example of a cylinder which is placed in a uniform electric field. Suppose this is a cylinder and it is placed in a uniform electric field. This cylinder has 3 surfaces. There are 2 circular cross sections, this one and this one, and one curved surface like this, curved surface. You can name these surfaces as, this circular cross section can be named as surface 1, this cross section can be named as surface 2, and you can name the curved surface as surface 3. Now, let us find the flux passing through this cylinder. So, to find the flux passing through this cylinder, we will just find the flux through these 3 surfaces, and the total flux will be the flux through surface 1 plus flux through surface 2 plus flux through surface 3. Now, from the figure you can clearly observe that for surface 3 at every point electric field is tangential to the surface, electric field is tangential to the surface, and angle between electric field and normal to the surface is 90 degree. So, flux through the curved portion phi 3 will be E S 3 cos 90, and cos 90 is 0. So, the flux through the curved surface is 0. So, the surface 3 does not contribute to electric flux. Now, if we look at surface 1, the outward normal to the surface 1 is towards left, that is in a direction opposite to the direction of electric field. So, the angle between electric field and normal for the surface 1 is 180 degree, and for surface 2 outward normal is in the direction of electric field, and angle between electric field and normal is 0 degree for surface 2. So, the flux for surface 1 will be E is the electric field, and let us suppose the area of this surface is A and cos 180, and cos 180 degree is -1. So, we get minus E A. Similarly, we can get flux flow for surface 2, which is E A cos 0, because normal and electric field are in the same direction and cos 0 is 1. So, flux will be plus E A. Hence, the net flux passing through this cylinder will be the sum of the flux through three surfaces, phi 1 plus phi 2 plus phi 3, which is minus E A plus E A plus 0 is equal to 0. Thus, the total flux is 0 as expected by Gauss law. Thus, whenever you find that the net electric flux through a closed surface is 0, we conclude that the total charge contained in the closed surface is also 0. The great significance of Gauss's law is that it is true in general for any arbitrary surface which is enclosing a charge, and not only for the simple cases we have discussed. Let us note some important points regarding this law. Gauss's law is true for any closed surface, no matter what its shape or size. The term Q on the right side of Gauss's law, where flux is Q by epsilon naught, this Q on the right side of Gauss's law includes the sum of all charges enclosed by the surface. The charges may be located anywhere inside the surface. In the situation when the surface is so chosen that there are some charges inside and some outside, then the electric field whose flux appears on the left side of it is due to all the charges both inside and outside the surface S. The term Q on the right side of Gauss's law, however, represents only the total charge inside S. The surface that we choose for the application of Gauss's law is called Gaussian surface. You may choose any Gaussian surface and apply Gauss's law. However, take care not to let the Gaussian surface pass through any discrete charge. This is because electric field due to a system of discrete charges is not well defined at the location of any charge. This is because electric field due to a system of discrete charges is not well defined at the location of any charge. As you go close to the charge, the field grows without any bound. However, the Gaussian surface can pass through a continuous charge distribution. Gauss's law is often useful towards a much easier calculation of electrostatic field when the system has some symmetry. This is facilitated by the choice of a suitable Gaussian surface. Finally, Gauss's law is based on the inverse square dependence on distance contained in the Coulomb's law. Any violation of Gauss's law will indicate departure from the inverse square law. Let us now try to solve some problems based on electric flux. Careful measurements of electric field at the surface of a black box indicate that the net outward flux through the surface of the box is 8 into 10 to the power 3 Newton meter square per Coulomb. Now, you have to find what is the net charge inside the box. The second part of the problem says, if the net outward flux through the surface of the box were 0, could you conclude that there were no charges inside the box? Why or why not? So, let us start by part first of this problem, in which you have to find the net charge inside the box, where you are given electric flux which is 8.0 into 10 to the power 3 Newton meter square per coulomb, and you have to find the net charge enclosed by the box. Now, from Gauss's law, you know that total electric flux passing through a surface is equal to amount of charge enclosed by the surface divided by epsilon naught. From this formula, you can easily find the amount of charge enclosed by the surface is phi multiplied by epsilon naught, where the value of flux is given to you in the question, and the value of epsilon naught, that is electrical permittivity of free space, is, we know that it is 8.85 into 10 to the power minus 12 coulomb square per Newton per meter square. By putting these values of phi and epsilon naught, you can easily get the amount of charge enclosed by this black box. Now, let us look at the second part of this problem, which says if the net outward flux through the surface of the black box were 0, that means if phi would have been 0, could you conclude that there were no charges inside the box? So, again we see that Q is equal to phi multiplied by epsilon naught, where Q is net charge, Q is the net charge enclosed. Remember that Q is not the charge enclosed. Focus on this word net. It is the net amount of charge enclosed by the surface. That means, if phi is 0, implies the net amount of charge, that is Q net, is 0. But it does not imply that the surface does not contain any charge. There may be charges of opposite signs, such that the surface may contain a dipole. For example, this is any surface and it may contain an electric dipole, and you can clearly see that the net charge, the sum of these two charges, is still 0. That means, in such a case, when the net charge is 0, flux passing through the surface will be 0. It means, if flux passing through the surface is 0, net charge enclosed by the surface is 0, but surface may contain charges of opposite signs in such a way that their sum comes out to be 0. Now, have a look at another problem. A point charge plus 10 microcoulomb is at a distance of 5 centimeter directly above the center of a square of side 10 centimeter. As shown in figure, what is the magnitude of the electric flux through the square? So, to find the net flux through this square, think the square as one of the face of a cube. Suppose this is a cube, you may consider this sphere as this face, the lower face of this cube, this square may be considered as the base of this cube. You may erect walls on the 4 sides of this cube, and you can cover it with a lid like this, so that you get a complete cube. In this way, this charge q will come at the center of this cube. Now, the total flux passing through this cube will be amount of charge enclosed divided by epsilon naught, where charge is 10 microcoulomb. Now, because there are 6 faces in a cube and each face has an area equal to the area of this square. So, the flux through each face of this cube will be flux through single phase of this cube, you can call it phi single, it will be 1 by 6 of q by epsilon naught, and this will be the flux passing through this square. Now, putting the value of q and epsilon naught, you can solve it to find the flux passing through this square, and flux will become 1 by 6 of q by epsilon naught. You can do one more simple thing to make the calculation easier. Whenever you get epsilon naught in the denominator side, you can just multiply and divide by 4 pi, so that it becomes 1 by 6 into 1 by 4 pi epsilon naught into 4 pi into q. This is the flux through single face of the cube, that is 1 by 6 into, and we know the value of this constant is 9 into 10 to the power 9, 4, pi is 22 by 7, and your charge was 10 microcoulomb, that is 10 into 10 to the power minus 6. This way you can find the flux through each face of this cube, which is the flux passing through the square in question, and you can put the final answer by writing unit as Newton meter square per coulomb. In this program, we discussed Gauss's law, which can be used to find electric flux passing through a surface. Can you use this law to find electric field due to a uniformly charged conducting sphere, or infinitely long straight uniformly charged wire, or due to a uniformly charged infinite plane sheet? Just think over it and try it. Thank you.